Good morning, everyone. I warmly welcome you at our webinar series of webinars. And today we have a pleasure to guest our Tom. For those who don't know Tom yet, I wanted to introduce our wonderful chief medical physicist. And his contribution is enormous and in product development, user manuals development, or every day-to-day troubleshooting during quality control procedures and testing. This is the invaluable word of his work and his person. And perhaps some of you only can say more. And today we will be talking about the quality assurance in computed tomography. So I can pass the voice to Tom. Tom,
Okay, thank you, Arthur. My name is Tomasz Kostecki. I worked for Diagnomatics for 3 years, and I've been helping in developing phantoms. Okay, so let's start my presentation. So computed tomography in focus. We all know CT scanners. There are the core of most diagnostic departments. But CTs have evolved far beyond that. What is a CT? Computed tomography is a device that uses X-ray acquired from multiple angles around the patient to create cross-sectional images. The key difference is from a standard X-ray is that CT scanners collect data from many angles, not just one. Okay, CT technology is no longer limited to conventional scanners. It is increasingly integrated into specialized devices across multiple clinical fields. In the image, you can see a standard CT scanner, a dental CBCT scanner, and C-arm with integrated CBCT, and a new device, a breast CBCT scanner. In nuclear medicine, the CT scanners are used for anatomical localizations to show the data from PET on the anatomy showed thanks to the CT scanner, and we get the combined images. And also for attenuation correction. For more information, check the Diagnomatic Academy on Nuclear Medicine, which was performed by my friend Christoph. Okay, CT in radiotherapy plays a critical role by enabling precise treatment planning and guidance. In the image, we can see quality phantoms for CT and CBCT. As there are many CT devices, every system has a dedicated phantom to ensure accuracy and quality. In the images, you can see ProCT for veterinary CT scanners, ProDent CBCT phantom for dental and not only dental uses, ProDent CT Mini for dental CBCT. This one is pro-MAM CBCT phantom. And finally, our most often used Pro-CT Mark II. Okay, so I mentioned CBCT, but what is it exactly? In the standard CT scanner, the radiation is shaped in a fan, and in the cone beam CT, the radiation field is shaped as a cone. The cone beam CT is a variant type of computer tomography. Although it has many advantages, the main two disadvantages are increased scatter radiation and cone beam artifact if an inappropriate reconstruction algorithm is in use. Increased scatter radiation occurs because unlike in a regular CT, in the cone beam CT, the beam isn't collimated. So as you can see, all the scatter radiation hits the panel detector anyway. As for the cone beam artifact, we had a it can occur if you don't use a proper reconstruction algorithm. A customer of ours sent us those images because he thought we sent him a broken phantom. So as you can see, the CT numbers in the image differ between images, right? So here we have a mean of 238, and in the last image is 400, is above 400. We checked the images, and in the sagittal plane, we've noticed that the cone beam artifact occurred. As you can see, there is this rooftop shaped artifact because of the shape of the cone. Right. So if you guide a couple of lines according to the stripes of the artifact, we can find the probable location of the X-ray tube. And here is a view from the coronal side. It was a CT, so the X-ray tube traveled from one side to another, and this made the rooftop artifact. You have to know your tools and your diagnomatic equipment, right? So it's very important that you know that. Okay, phantoms for most CTs. This is the simplest phantom for a CT scanner. The purpose of this phantom is to simulate the patient's body and to calculate the dose that the patient receives. To use this phantom, select appropriate phantom size. You can choose from the 32 diameter phantom or 16 diameter phantom on the inside. We also have a three pieces variant. So this one is 10 centimeters piece, which simulates a pediatric head. Okay, insert a ionization chamber into center of peripheral holes or the center one. Record those measurements and calculate using this equation. The peripheral should be the average of the 4 measurements. Now let's move to the quality phantoms. This is our Pro CT Mark II. And this phantom is built out of a couple of modules. This is the homogeneous module. We can use it for artifact test. The test is that we shouldn't see no artifacts in the image. An example of artifact had been sent to us from a customer. This could be those circle-shaped artifacts this was actually on a patient's body, so they didn't. It was occurring randomly, so they couldn't see it on the phantom, but they have seen it on patients. What else can we do with the homogeneous module? We can check the Hounsfield units value. It shouldn't vary more than 5 Hounsfield units from 0. We can also check the noise. We just use the ROI with approximate size of 40% of the phantom. The standard deviation in that region shouldn't differ more than 20% from the reference value. Okay, I would also like to mention that there is something that is called the peak KV dependency for all the materials, right? So the real water, the liquid, usually stays near the 0, but for the other materials, you will see variation in the according to the peak kilovolts. So this is a chart which shows the real water to solid water equivalent. So it doesn't always show true 0. Okay, next test with the uniformity model is the with the homogeneous model is the uniformity test. You place 5 rows in a cross, and the difference in the Hounsfield units value between the center and the sides should be constant in time. So you compare it to the reference value, and you get the results of the test. Okay, this is the low contrast model. This test depends on the legislation in your country. In some countries, you should be able to see the same number of the objects. In other countries, you should be able to see the objects of the exact size and contrast value. This is the sensitometric module. The values, the CT values should be constant over time. This is the high contrast module. It has a number of distinguishable high contrast objects, and they shouldn't differ over time. This module consists also of couple of elements to calculate the MTF function. In our new phantom, we moved the MTF elements to the geometry modules, so there would be less distortion because from the line pair elements. Geometry module is for verification of geometric accuracy of CT images. Distances between four rods, 1, 2, 3, 4, in horizontal and vertical, vertical and diagonal, shouldn't differ from actual values more than 1 millimeter. Another element in the geometry module are the ramps. One of the functions of the ramps is to measure slice thickness. Just measure the ramp length that you can see and divide it by 2, and then you will get the slice thickness. It shouldn't differ more than 20% from actually set value. CT in radiotherapy. Because even small misalignments can affect treatment accuracy, dedicated phantoms like the Pro-CT Align are used to verify laser to CT alignment. You just scan the phantom every day. You just place the phantom on the table, aligned with the lasers, and then scan it. The fiducials that are embedded in this phantom should be visible on the not further than 2 millimeters from the center slice. In radiotherapy, CT images are not only used for visualization, but also to calculate dose. This requires an accurate relationship between CT numbers and electron density. That is why we use Pro-RT at the phantom. Okay, how do you perform a test? We scan the phantom. This is actually a module that you can use in the Pro-CT Mark II. So we scan the phantom and using ROIs of the similar size, we check the mean pixel values. We should write them to a calculations sheet. Then find the electron density in the table we provide, and write them accordingly to the information from the scan. By doing that, you can calculate the linear regression for the data points between Hounsfield units and electron density. Usually you have to calculate A and B values from the equation, and then you insert your data to the treatment planning system. If you don't know how to do it, ask your vendor of your treatment planning system. And okay, another test we can perform in the radiotherapy is the Pro-Align cube. Pro-Align cube verifies the alignment of CBCT. CBCT are those two elements, and megawatt isocenters. Yes, because there are two devices actually, and they should point to the same. They should be centered in the same on the same point in a three-dimensional space. Okay, how do you perform a test like that? First, at the beginning, you do the preparation, so you scan the cube on the CT. You can create a treatment plan. You also need to create some DRRs, which are digitally reconstructed radiographs. This is an image that simulates two-dimensional radiograph, X-ray image. Okay, so every day you have to place the priority align cube on the table. But this time, instead of the center, you have to place it on the offset marks. Then you perform the cone beam CT of the image, and you compare it with the reference image that you got from the CT scanner from the preparation phase. If you align them correctly, you should get the offset that are exact as the values that the offset marks are moved to. Okay. After that, you take an image using the EPIT panel and the megavolt source. You take two pictures from 0 and 90 degrees, and then you also fuse the images from the treatment planning and the images you got today. They shouldn't vary more than 2 millimeters. Future of the diagnostic CTs. As CT evolves from anatomical imaging to material characterization, quality assurance must also evolve. This is where multi-energy phantoms become essential. Dual energy scanners can produce, for instance, iodine maps and virtual non-contrast images. Iodine maps help identify abnormal iodine distribution in the body, while the virtual non-contrast images reduce radiation dose by eliminating the need for a true non-contrast scan. So instead of two scans without the contrast and then with the contrast, we can take just one scan and we just calculate two sets of images. But we would like to check it, right? So this is where our multi-energy phantom comes into play. As you can see, we have multiple samples in the phantom, and we scan it with the CT scanner, and then we calculate the images. As you can see on the iodine images, for instance, this sample is pure white, and on the non-contrast image, the iodine was removed from the image. Okay, so as you can see, the CT has evolved from a diagnostic tool into a complex system used in diagnostic centers, therapy and advanced imaging. As complexity increases, quality assurance becomes essential. Diagnomatic phantoms ensure accuracy, safety, and confidence in every application. Okay, and that's all I have for today. So thank you.
Thank you, Tomasz. It was very very interesting, especially the timeline and how the imaging, digital imaging in 3D, going further and further. So from simple, because CT, I think it's when you go to the past, it's like 50 years old, 60 years old.
Yeah.
So, and for the last 40, 50 years, there was almost no improvements. It was almost the same image, the same technique you was using. Yeah, it was better and then more the resolution was better, the contrast were improved, but these days with the photon counting multi-energy scanners, it's a breakthrough and something new that I think will be a future in diagnostic imaging.
Hmm. That's right. Uh, we came a long way, right? Although the concepts of the, for example, dual energy CT scanners are dated back to, I guess, 70s. They are coming into play now, thanks to the computers, right?
Yes,
Because
yes,
we can do
I
the
think
calculations on the fly.
it's from the theory uh, to the real working machines. It's a long way, and still, on the other hand, I think that uh, the medical physicists, the radiology doctors, are not so 100% confident in the images that they receive from the new cutting edge machines, I guess.
Mhm.
It will
I guess.
still need some time to get used to believe in the new high tech technology.
Mhm. Yes, I think it should be a shift in the perspective of the diagnosis, as if they don't use it, uh, so the CT scanners may not be used as they are intended.
Yeah, yeah, it will take time because I think that the new devices are not so common yet. It's percent, 2% or 5% in the market. So still, you will not meet them on the daily basis. They are from place to place, and it will take time to be a standard, and
Mhm.
it will take time to familiarize with them.
Yeah,
Thank you so much, Tom.
thank
Thank
you.
you. Thank you all for having time and spending it with us. And I warmly invite you for the next session and for our tomorrow webinar also. Thank you and bye bye.